Early March 1945. Lechfeld Air Base, Bavaria, Germany. Oberfeldwebel Klaus Neumann stood in the maintenance hangar of WWII 7, staring at something that should not have been possible. The Messerschmitt Me262 jet fighter before him had completed exactly 9 flight hours since engine installation. 9 hours. The turbine blades in both Junkers Jumo 004 engines had already begun catastrophic deformation. Through the open engine cowlings, Neumann could see what every Luftwaffe mechanic had learned to recognize with sickening familiarity. The turbine blades showed visible warping. Metal that should have maintained precise aerodynamic profiles had twisted under operational heat. Some blades exhibited hairline cracks, others had already fractured completely. The revolutionary jet engines that were supposed to restore German air superiority were consuming themselves from within. This was not battle damage. No enemy fire had touched this aircraft. This was simple operation under normal conditions. Flight time that would barely register as break-in period for a conventional piston engine had destroyed these jet power plants completely. Both engines required immediate replacement. Without replacement, the next flight would almost certainly end in catastrophic failure, probably killing the pilot. Neumann had seen this pattern dozens of times since WWII 7 began Me262 operations in August 1944. Every mechanic in the unit knew the terrible arithmetic: 10 to 25 flight hours maximum before engine replacement became mandatory. Sometimes less if pilots pushed the engines hard during combat. The most advanced fighter aircraft in the world was being crippled not by Allied fighters, not by overwhelming numbers, but by engines that self-destructed through normal operation. What would emerge from the desperate struggle to keep Me262s operational would reveal a fundamental contradiction at the heart of German technological development in the final years of the war. Germany possessed the scientific knowledge and engineering skill to create revolutionary weapons. The Me262 represented genuine innovation, the world's first operational jet fighter, capable of speeds exceeding 540 miles per hour, faster than any Allied piston engine fighter could achieve. But Germany lacked the industrial resources, specifically the rare alloying metals necessary to build engines that could withstand the extreme temperatures and stresses of jet propulsion for more than a few hours. The result was a weapon system that looked magnificent on paper and in propaganda, impressed everyone who saw it fly, and fundamentally failed to achieve strategic impact because it could not be sustained in combat operations. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching. From today, the Messerschmitt Me262 emerged from Germany's response to inevitable Allied air superiority. By 1943, Luftwaffe leadership recognized that conventional piston engine fighters, regardless of performance improvements, could not overcome the numerical and industrial advantages Allied air forces possessed. Jet propulsion offered the possibility of performance so superior that quality might compensate for quantity. The concept was not new. Jet engine development had proceeded in both Germany and Britain throughout the late 1930s. Frank Whittle in Britain and Hans von Ohain in Germany developed working jet engines independently and nearly simultaneously. However, Germany moved faster from experimental prototypes to operational aircraft. The Heinkel He-178 made the world's first jet-powered flight on August 27, 1939, just days before Germany invaded Poland. This historic flight validated jet propulsion but revealed enormous technical challenges. The Heinkel engine produced approximately 1,100 pounds of thrust, but lasted only minutes before overheating failures occurred. Von Ohain and his engineering team at Heinkel understood immediately that heat management represented the fundamental challenge. Jet engines operate at temperatures far exceeding piston engines. The combustion chamber of a turbojet reaches temperatures approaching 2,000 degrees Fahrenheit. Turbine blades, which extract energy from the exhaust gases to drive the compressor, operate continuously in gas streams exceeding 1,500 degrees Fahrenheit, while spinning at 10,000 to 12,000 revolutions per minute. Materials capable of withstanding these conditions while maintaining structural integrity and precise dimensional stability simply did not exist in common industrial metals. Pre-war metallurgical research had identified alloying elements that could create heat-resistant steels capable of surviving jet engine conditions. Nickel, chromium, molybdenum, and cobalt, when added to steel in specific percentages, dramatically increased high-temperature strength and resistance to creep. The gradual deformation of metal under sustained stress at elevated temperatures. British metallurgists developed mnemonic alloys incorporating these elements specifically for jet engine applications. These specialized alloys could withstand turbine operating conditions for hundreds of hours before requiring replacement. Germany possessed the metallurgical knowledge. German scientists understood heat-resistant alloy chemistry as well as their British counterparts, but Germany lacked access to the raw materials in quantities necessary for mass production. Nickel came primarily from Canada and the Soviet Union. Germany lost access to Canadian nickel when Britain declared war. Soviet nickel supplies were cut off when Germany invaded the Soviet Union in June 1941. Chromium came from Turkey, Southern Africa, and the Soviet Union. Turkish supplies were limited and competed with other industrial demands. German-controlled chrome mines in occupied territories provided some supply, but not enough for all requirements. Molybdenum deposits existed primarily in the United States and Norway. Allied bombing destroyed German access to Norwegian molybdenum in 1943. The result was a materials crisis that shaped every aspect of German jet engine development. Engineers at Junkers Motoren, the company that developed the Jumo 004 engine for the Me262, faced an impossible requirement. Design a turbojet engine capable of producing thrust sufficient to power a fighter aircraft to combat effective speeds using materials available in a blockaded, resource-starved economy. The solution they developed was ingenious, desperate, and fundamentally unsustainable. Junkers engineers used mild steel for turbine blades, steel with minimal alloying elements. This material could be produced from German domestic iron and available scrap metal. It cost far less than exotic heat-resistant alloys and required no imported materials. The problem was simple and insurmountable. Mild steel cannot withstand jet engine operating temperatures for extended periods. The engineering team knew this. Test data from prototype engines made the limitations brutally clear. Dr. Anselm Franz, chief engineer for the Jumo 004 program, later testified to Allied interrogators that turbine blade life expectancy was understood to be approximately 10 to 25 hours under normal operating conditions from the earliest development stages. This was not a manufacturing defect or unexpected failure mode. It was the known, accepted, inevitable consequence of using inadequate materials because proper materials were unavailable. German engineers implemented every possible design modification to extend engine life within the constraints imposed by material limitations. They used hollow turbine blades to reduce weight and thermal mass. They implemented sophisticated cooling air passages to reduce blade temperatures. They carefully optimized turbine rotational speeds to minimize stress while maintaining adequate thrust. They developed maintenance procedures allowing rapid engine changes to minimize aircraft downtime. These modifications helped but could not overcome fundamental material inadequacy. A mild steel turbine blade operating continuously in 1,500 Fahrenheit gas streams while spinning at 12,000 revolutions per minute will deform. The metal creeps, losing dimensional stability. The precise aerodynamic profiles necessary for efficient energy extraction degrade. Eventually, blades crack and fracture. When that happens during flight, catastrophic engine failure occurs. The Me262 program proceeded despite these known limitations, because German military leadership believed, or desperately hoped, that revolutionary performance would compensate for mechanical fragility. The Me262 prototype first flew on July 18, 1942, using piston engines because jet engines were not yet ready. The first flight using Jumo 004 jet engines occurred on July 18, 1942, exactly 1 year later. The aircraft's performance exceeded expectations. Maximum speed reached 540 miles per hour in level flight, approximately 150 miles per hour faster than the best Allied piston fighters. Rate of climb exceeded 4,000 feet per minute, far superior to conventional fighters. The aircraft handled well despite its revolutionary design. Test pilots praised the smooth, vibration-free power delivery compared to piston engines. Hermann Göring, commander of the Luftwaffe, witnessed demonstration flights and immediately demanded mass production. Adolf Hitler, shown films of Me262 flights, became personally convinced that this weapon would restore German air superiority and demanded maximum priority for the program. Production authorization came in November 1943 with initial orders for 60 aircraft. This increased to over 1,000 by May 1944 as Hitler became increasingly obsessed with jet fighters as war-winning weapons. Messerschmitt factories at Regensburg and other locations began mass production. By war's end, approximately 1,400 Me262s had been completed. The production numbers seemed impressive, but masked the underlying crisis. Every Me262 required Jumo 004 engines. Every Jumo 004 had approximately 10 to 25-hour service life. This meant that operational Me262 units required continuous engine production and replacement at rates far exceeding anything required for piston engine fighters. A conventional Luftwaffe fighter unit operating Focke-Wulf Fall 190 fighters might expect engine overhauls every 150 to 200 flight hours. Major engine failures requiring complete replacement occurred perhaps every 400 to 600 hours. This meant a fighter group of 40 aircraft might require 10 to 15 engine replacements monthly under intensive operations. A jet fighter unit operating Me262s required engine replacements every 10 to 25 hours. The same 40 aircraft group needed approximately 80 to 100 engine changes monthly just to maintain operational status, assuming intensive combat operations. This was not sustainable. Junkers factories produced approximately 5,000 Jumo 004 engines during the war. This sounds substantial until operational mathematics are applied. 1,400 Me262s, each equipped with 2 engines, required 2,800 engines for initial installation. The remaining 2,200 engines provided enough replacements for approximately 11 flight hours per aircraft, averaged across the entire production run. 11 hours, assuming perfect logistics, no engines lost to Allied bombing, no transportation problems, and immediate replacement whenever engines reached end of life. The operational reality proved even worse than these calculations suggested. Me262 units began forming in summer 1944. WWII 7 became the first operational jet fighter unit, achieving initial operational capability in August 1944. Commando Nowotny, an experimental unit led by Major Walter Nowotny, began operations in September 1944. Additional units formed through early 1945 as more aircraft became available. These units immediately encountered the engine life crisis. Commanders received explicit instructions from higher headquarters about engine limitations. Technical orders specified maximum flight time before mandatory engine replacement. 10 hours was the minimum guaranteed life. 25 hours represented optimistic maximum under ideal conditions. Combat operations, which required maximum power settings and thermal stress, reduced engine life toward the 10-hour minimum. Unit war diaries documented the resulting operational paralysis. WWII 7 records from October 1944 show 38 Me262s assigned on paper, but typically only 12 to 15 actually operational on any given day. The remainder sat grounded, awaiting engine replacement. Spare engines arrived irregularly, disrupted by Allied bombing of transportation networks. One particularly revealing entry from November 3 1944, noted that 4 aircraft had been grounded that morning after pilots reported rough engine running and vibration. Inspection revealed turbine blade deformation in all cases. All 4 aircraft required both engines replaced. 8 engines were needed immediately. Only 3 spare engines were available at the base. 5 engines were supposedly in transit from Junkers factories, but transportation delays meant arrival time was unknown. 4 valuable aircraft, pilots ready and trained, sat useless until engines arrived. The entry concluded with a simple statement capturing the frustration of mechanics and commanders. Our jets are magnificent when they fly. They rarely fly because engines constantly fail. Maintenance crews developed brutal familiarity with engine replacement procedures. Junkers engineers had designed the Jumo 004 for relatively rapid removal and installation, recognizing that frequent changes were inevitable. An experienced crew could remove a failed engine and install a replacement in approximately 4 to 6 hours, assuming proper tools and equipment. This seems efficient until cumulative time is calculated, with 40 aircraft requiring engine changes every 10 to 25 flight hours. Maintenance crews spent enormous time just replacing engines that had reached end of service life, even when nothing else was wrong with the aircraft. Klaus Neumann, the Oberfeldwebel mentioned in the opening, later described the psychological impact on maintenance personnel. We were not repairing battle damage. We were not fixing systems broken by Allied guns. We were constantly replacing engines that had simply worn out through normal operation. The engines destroyed themselves. Every mechanic understood that the turbine blades could not handle the heat and stress. We used mild steel because we had nothing better. The steel deformed. The blades warped and cracked. There was nothing we could do to prevent it. We just replaced engines constantly and hoped more engines would arrive before we ran out. The engine life crisis prevented the Me262 from achieving anything approaching its theoretical combat potential. German propaganda celebrated the jet fighter as a revolutionary weapon. Newsreels showed Me262s racing past Allied bombers at incredible speeds. The imagery was impressive and real. Individual Me262 pilots achieved remarkable successes when they could fly. Oberstleutnant Heinz Baer scored 16 kills in Me262s. Major Georg Peter Eder scored 12. Several other pilots achieved multiple kills. These successes validated the aircraft's performance advantages. A jet fighter traveling 150 miles per hour faster than enemy fighters possessed enormous tactical advantages. But individual successes could not overcome systemic operational paralysis imposed by engine unreliability. Allied bomber streams continued reaching German targets throughout late 1944 and early 1945. Me262 interceptions remained sporadic and limited because most jets sat grounded, awaiting engines or undergoing engine replacement. The mathematical reality was inescapable. If a jet fighter unit possessed 40 aircraft but could keep only 12 operational due to engine shortages, the unit's effective strength was 12 aircraft, regardless of paper strength. German Fighter Command planned operations based on paper strength, then discovered actual strength was less than 1/3 of planning assumptions. Missions were scrubbed or reduced in scale because insufficient aircraft were operational. Adolf Galland, General der Jagdflieger, and one of Germany's most accomplished fighter pilots, recognized the crisis early. Galland had advocated strongly for jet fighter development and pushed for maximum Me262 production. However, after observing operational realities through late 1944, he became deeply concerned about the program's viability. In December 1944, Galland submitted a report to Hermann Göring, detailing the engine problem explicitly. The report, recovered by Allied forces after the war, and translated for intelligence analysis, stated clearly that Me262 operational availability averaged 30 to 35%, due almost entirely to engine limitations. Galland calculated that Germany was producing approximately 400 Me262s monthly by December 1944, but needed to produce approximately 1,500 Jumo 004 engines monthly just keep existing aircraft operational. Actual engine production was approximately 600 units monthly. This deficit meant that operational rates would decline over time, as accumulated engine failures outpaced replacement engine availability. Galland recommended either dramatically increasing engine production or reducing aircraft production until engine supply could support sustainable operations. The report was ignored. Hitler remained fixated on aircraft numbers rather than operational sustainability. The disconnect between aircraft production and engine production revealed fundamental flaws in German strategic planning. Messerschmitt factories could produce Me262 airframes relatively efficiently. The basic aircraft, excluding engines, was not extraordinarily complex compared to piston engine fighters. Production rates reached approximately 120 aircraft monthly by early 1945, but Jumo 004 production faced severe constraints. The engines required precision manufacturing with tight tolerances. Turbine blades, even mild steel blades, needed careful machining and balancing. Combustion chambers required specialized welding and heat treatment. Assembly demanded skilled labor and quality control. Allied bombing systematically targeted German engine factories. Junkers' facilities at Dessau faced repeated attacks throughout 1944. Attacks in May and June 1944 reduced production by approximately 40% for 3 months. Subsequent attacks in September and October further disrupted output. Dispersal of production to smaller facilities helped but reduced efficiency and complicated quality control. The cumulative effect was a growing gap between aircraft availability and engine availability. By January 1945, German records indicate approximately 450 Me262s were in Luftwaffe inventory. However, operational availability was approximately 120 aircraft, roughly 27%. The remaining 330 aircraft sat grounded, awaiting engines or undergoing engine replacement. American intelligence received detailed information about Me262 engine problems through multiple channels beginning in late 1944. Shot down Me262 pilots, captured and interrogated, provided technical information about engine limitations. Several pilots volunteered information freely, apparently frustrated by the operational constraints imposed by engine unreliability. One interrogation report from December 1944 quoted a captured lieutenant from WWII 7 describing the engine situation bluntly. The Me262 is the finest fighter in the world when it has working engines. It rarely has working engines. Every pilot knows that engines must be changed after 10 to 20 hours. Sometimes we land after a mission, and mechanics tell us both engines must come out immediately. The aircraft is grounded until new engines arrive. Sometimes this takes days, sometimes weeks. We have many jets, we have few engines. This makes us helpless. British intelligence obtained even more detailed information through Operation Crossbow and related technical intelligence programs. British commandos and intelligence officers in occupied Europe established networks of informants, including forced labourers at German aircraft factories. These sources provided detailed reports about production problems, quality issues, and specific technical limitations. One particularly valuable report from February 1945 came from a Czech engineer who was forced to work at a Junkers engine facility. The report, smuggled to British intelligence through resistance networks, described in detail the materials crisis affecting engine production. The engineer explained that Junkers had attempted to develop improved heat-resistant alloys using available materials, but had achieved only marginal improvements. Experimental turbine blades using modified steel compositions extended life to perhaps 30 to 40 hours under ideal conditions. But these improved alloys required small quantities of scarce materials that were unavailable in sufficient supply for mass production. The engineer estimated that fewer than 10% of engines received improved blades. The remainder used standard mild steel with 10 to 25-hour life expectancy. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Allied air forces adjusted their tactics based on intelligence about Me262 limitations. American bomber commanders recognized that jet fighters posed serious threats when operational, but appeared in limited numbers due to engine-related operational constraints. Tactical guidance distributed to bomber groups emphasized that Me262 attacks typically involved small formations of 4 to 8 aircraft rather than large formations. This reflected operational reality rather than tactical preference. Jet units could rarely launch more than 8 to 12 aircraft simultaneously because engine problems kept most assigned aircraft grounded. Fighter escort tactics evolved to counter the speed advantage jet fighters possessed. American P-51 Mustang fighters could not match Me-262 speed in level flight or climbing. However, American pilots learned that Me-262s were vulnerable during takeoff and landing when speed advantages disappeared. Attacks on jet airfields during takeoff and landing phases became standard tactics. Me-262 pilots were forced to time operations carefully, taking off only when escort fighters could provide cover during vulnerable phases. This defensive requirement further reduced operational flexibility. Intelligence about engine problems informed strategic bombing target selection. Junkers engine factories received high priority throughout late 1944 and early 1945. Transportation networks carrying engines from factories to operational units became priority targets. Supply depots storing spare engines were bombed when identified. The systematic campaign against Me-262 logistics prevented Germany from ever achieving the operational jet fighter strength that aircraft production numbers suggested should have been possible. The captured Me-262 aircraft that fell into Allied hands provided physical confirmation of intelligence reports about engine problems. American forces captured their first complete Me-262 at Rhine Airfield on April 1, 1945. The aircraft was nearly intact, with both engines installed, though not operational. British forces captured multiple Me-262s at various locations through April and May 1945 as Germany collapsed. Several aircraft were shipped to Britain and the United States for comprehensive testing and evaluation. The most detailed technical analysis was conducted at Wright Field in Dayton, Ohio, where captured aircraft and engines were sent for evaluation by American aviation engineers. Testing began in June 1945 and continued through late 1946. The American evaluation team included metallurgists, propulsion engineers, and experienced test pilots. Colonel Harold Watson led the evaluation program. His team's mandate was comprehensive. Understand Me-262 performance characteristics, evaluate German jet engine technology, identify weaknesses and vulnerabilities, and extract lessons applicable to American jet development programs. The engines received particular attention because intelligence reports had emphasized engine limitations as the Me-262's primary weakness. American metallurgists conducted detailed analysis of JUMO 004 turbine blades. Spectroscopic analysis determined precise chemical composition. The results confirmed intelligence reports. The turbine blades were manufactured from low-alloy steel, containing approximately 0.2% carbon, 1% chromium, and trace quantities of other elements. This composition provided minimal high-temperature strength. Comparative analysis with British jet engines revealed the magnitude of material quality differences. British Rolls-Royce Welland engines, which powered the Perth Gloucester Meteor jet fighter, used mnemonic alloy turbine blades containing approximately 20% chromium, 20% nickel, and smaller quantities of molybdenum and titanium. This composition provided high-temperature strength approximately 3 to 4 times greater than German mild steel blades. The practical result was dramatic. Rolls-Royce Welland engines achieved operational lives exceeding 150 hours before requiring major overhaul. Some engines ran reliably for over 300 hours. This gave British jet fighters operational sustainability comparable to piston engine fighters. Engine changes remained necessary, but at intervals permitting normal operational planning and maintenance scheduling. American engineers calculated that if Germany had possessed access to proper alloying materials and had manufactured JUMO 004 turbine blades from heat-resistant steel comparable to British alloys, engine life would have extended to approximately 100 to 150 hours. This would have transformed Me262 operational viability completely. A jet fighter unit with 150-hour engine life could maintain normal operational rates. Aircraft would fly 10 to 15-hour missions multiple times before requiring engine changes. Maintenance planning would be predictable. Spare engine requirements would be manageable. The Me262 would have achieved its potential as a revolutionary weapon system. But Germany did not possess proper materials. German engineers understood exactly what was needed but could not obtain it. The result was a weapon system crippled by materials science limitations that no amount of engineering cleverness could overcome. The Wright Field Report, completed in October 1946, concluded that the Me262 represented remarkable achievement in aeronautical engineering, operating under severe resource constraints. The airframe design was sound and efficient. The engines, while limited by materials, demonstrated sophisticated engineering and clever solutions to difficult problems. However, the aircraft's operational effectiveness was fundamentally compromised by engine limitations that were inevitable given German access to materials. The report recommended that American jet development programs prioritize engine reliability and durability equally with thrust and performance. This recommendation directly influenced American turbojet development throughout the late 1940s and 1950s. The principle that operational sustainability matters as much as maximum performance became foundational to American jet engine design philosophy. Every American jet engine developed after World War II incorporated this lesson. Engines were designed for durability and maintainability from the beginning rather than maximum performance at any cost. The General Electric J-47 turbojet, which powered the F-86 Sabre fighter and numerous other aircraft beginning in 1949, was specifically designed for 150-hour time between overhaul as a minimum requirement. The engine achieved this reliability partly because American designers had full access to high-temperature alloys containing adequate nickel, chromium, and molybdenum. The Pratt & Whitney J-57 turbojet, introduced in 1953, and eventually powering over 30 different aircraft types, emphasized durability even more strongly. Design requirements specified 300-hour time between overhaul with engines expected to achieve 1,000 hours total life before retirement. These requirements reflected lessons learned from Me262 analysis. Superior performance without durability creates weapons that cannot be sustained operationally. The Korean War validated these design principles decisively. American F-86 Sabres equipped with J-47 engines maintained operational availability rates exceeding 70% throughout the conflict. Engine problems occurred but rarely grounded aircraft for extended periods. Spare engines were available in adequate quantities because engine life was predictable and replacement intervals were manageable. Contrast this with hypothetical Korean War scenario where American jets suffered Me262 engine life problems. If F-86 engines lasted only 10 to 25 hours, operational availability would have collapsed. Entire fighter wings would have been grounded awaiting engines. The air superiority that F-86 seconds achieved over MiG-15 seconds would have been impossible to sustain. The Me262's legacy extended beyond engine design into broader military technology philosophy. The principle that emerged from studying German jet fighters became known informally among American defense planners as the sustainability principle. Advanced technology must be sustainable in extended operations, or it provides no strategic advantage regardless of tactical superiority. This principle was applied systematically to weapons development across all domains. Naval vessels were designed with maintenance accessibility as a primary requirement. Ground combat vehicles emphasized reliability and field maintainability. Aircraft of all types incorporated durability requirements into initial design specifications. The sustainability principle became so thoroughly integrated into American military procurement that its origin in World War II, German jet fighter analysis, was often forgotten. Universities teaching engineering management continue using the Me262 as a case study in systems engineering and technology development. The case examines how material constraints can limit technology implementation regardless of theoretical understanding. German engineers understood jet propulsion theory completely. They designed excellent airframes and reasonably effective engines given available materials, but they could not overcome material shortages that made sustained operations impossible. Business schools use the Me262 to illustrate how organizational culture and strategic priorities can lead to counterproductive decisions. German leadership prioritized maximum performance and revolutionary technology over operational sustainability. This produced impressive weapons that looked magnificent but could not be sustained in combat. American leadership prioritized adequacy sustained over time rather than excellence that could not be maintained. The different approaches produced different outcomes. Germany built approximately 1,400 Me262s that achieved limited strategic impact because they could rarely fly. The United States built approximately 15,000 jet aircraft of various types between 1945 and 1950 that maintained high operational availability because engines were reliable and sustainable. The final German production statistics reveal the magnitude of the Presalate strategic failure. Approximately 1,400 Me262s were completed between July 1944 and April 1945. German sources estimate that these aircraft collectively achieved approximately 50,000 flight hours total across all aircraft and all pilots throughout the war. This averages to approximately 36 flight hours per aircraft produced. However, this average is misleading because many aircraft were destroyed or captured before accumulating significant flight time. Aircraft that survived longer averaged perhaps 60 to 80 flight hours before war's end, but even 80 hours represented only 3 to 4 engine changes per aircraft position. The engines consumed themselves faster than combat consumed the aircraft. Compare this with American jet aircraft production and operations in the immediate post-war period. The Lockheed P-80 Shooting Star, America's first operational jet fighter, entered service in early 1945. Approximately 1,700 were produced through 1948. These aircraft collectively achieved approximately 400,000 flight hours during their service lives. This averages to approximately 235 flight hours per aircraft. The dramatic difference in average flight hours per aircraft reflects the cumulative impact of engine reliability. American jets could fly regularly and accumulate hours because engines lasted long enough to make regular operations possible. German jets sat grounded most of the time because engines failed too quickly to sustain operations. Klaus Neumann, the Luftwaffe mechanic introduced at the beginning, survived the war and was briefly held as a prisoner before release in late 1945. He returned to Bavaria and eventually provided testimony to American historical researchers documenting Luftwaffe jet operations. His account, recorded in 1953, provided detailed personal perspective on the engine crisis. Neumann described the psychological impact on maintenance crews of constantly fighting a losing battle against engine failures. We knew the engines would fail. Every mechanic knew mild steel turbine blades could not survive jet engine temperatures for long. We inspected engines after every flight, looking for blade deformation. When we found it, and we always found it eventually, we removed the engine and installed another. Then we waited for the next engine to fail. It was inevitable. There was nothing we could do to prevent it. We could only replace engines and hope more engines would arrive before we ran out completely. The frustration extended beyond mechanics to pilots. Trained jet pilots sat idle because their aircraft had no engines. Missions were planned then cancelled because engines failed during pre-flight checks. The revolutionary aircraft that was supposed to restore German air superiority spent most of its time grounded. Neumann's testimony captured the bitter irony. "We had the best fighter in the world. We could not use it because the engines destroyed themselves. The Allies did not need to shoot down our jets. They just had to wait. The engines would fail on their own." The post-war interrogations of German engineers and designers provided the final pieces of the Me262 story. Dr. Anselm Franz, the Junkers engineer who led Jumo 004 development, was extensively interviewed by American and British technical intelligence teams between May and August 1945. His testimony, documented in multiple reports now housed at the National Archives, revealed the full scope of the tragedy. Franz explained that his engineering team understood from the beginning that mild steel turbine blades would fail quickly. They calculated expected service life at approximately 10 to 25 hours during initial design phases in 1942. This was not unexpected failure. It was predicted outcome based on known material properties and operating conditions. Franz and his team repeatedly requested access to heat-resistant alloys. They submitted detailed technical requirements to German procurement authorities, explaining exactly what materials were needed and why. The requests were acknowledged but never fulfilled. Germany simply did not possess adequate quantities of nickel, chromium, and molybdenum. What small quantities existed were allocated to other critical military programs. Faced with impossible choices, Franz's team proceeded with mild steel because they had no alternative. They implemented every possible design modification to extend engine life within material constraints. They optimized blade cooling, reduced operating temperatures where possible, and developed maintenance procedures for rapid engine replacement. But they could not overcome fundamental material inadequacy. Franz's most revealing statement came near the end of his interrogation. "We built the best jet engine possible with the materials available to us. We knew it was inadequate. We knew engines would fail quickly. We reported this to military authorities. They ordered us to proceed anyway. They believed that even limited jet fighter capability was better than no jet capability. Perhaps they were correct, perhaps not. The engines failed exactly as we predicted they would fail." The Me262's operational record supports Franz's pessimistic assessment. German sources estimate that Me262s achieved approximately 500 confirmed aerial victories during the war. This sounds impressive until placed in context. 500 victories from approximately 1,400 aircraft produced represents 0.35 victories per aircraft. Many Me262s never flew combat missions because they were destroyed on the ground, captured before becoming operational, or could not fly due to engine problems. For the aircraft that did achieve combat operations, the kill ratio was better, but still disappointing given the aircraft's theoretical advantages. Experienced pilots in properly functioning Me262s could dominate Allied piston engine fighters. The speed differential was simply too great for conventional fighters to counter effectively. However, most Me262s sat grounded most of the time. The strategic impact was negligible. Allied bombing of Germany continued unabated throughout late 1944 and early 1945. Me262 interceptions caused losses but could not stop the bombing campaign. Allied air superiority over German territory was never seriously threatened. The revolutionary jet fighter that was supposed to change the war's course became a footnote, remembered more for its potential than its actual achievements. The surviving Me262s in museums today stand as monuments to engineering ambition constrained by industrial reality. The Smithsonian National Air and Space Museum displays a restored Me262. The aircraft looks impressive with its swept wings and streamlined design. The Jumo 004 engines, preserved in their nacelles, appear sophisticated and advanced. But the turbine blades inside those engines are mild steel, inadequate for sustained operations, capable of perhaps 20 hours before inevitable failure. Modern visitors admiring the aircraft rarely understand this fundamental limitation. They see the first operational jet fighter, a revolutionary aircraft that pioneered technologies still used today. What they cannot see is the metallurgical crisis that crippled operations, the material shortages that made sustainability impossible, and the strategic failure that resulted from building advanced weapons without the industrial resources to sustain them. The lesson remains relevant to contemporary military technology development. Advanced capabilities mean nothing without sustainable logistics. Revolutionary performance provides no strategic advantage if it cannot be maintained in extended operations. The finest weapon in the world becomes useless when it cannot be kept operational due to resource constraints or design limitations. The Me262 proved this principle definitively, through thousands of grounded aircraft, through tens of thousands of failed turbine blades, through the bitter frustration of pilots and mechanics who possessed a magnificent weapon they could rarely use. German engineering created a tactical masterpiece. German industry could not sustain it. The gap between theoretical capability and operational reality determined the outcome. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The Messerschmitt Me262 sits today in climate-controlled museums, its Jumo 004 engines silent forever. The turbine blades that could withstand only 10-25 hours of operation will never spin again. But the lessons it taught continue resonating through every engineering school, every military staff college, every defense procurement office studying modern warfare technology. The principles are timeless. Superior specifications on paper cannot overcome inadequate materials in practice. Revolutionary performance without operational sustainability equals strategic failure. The most advanced technology in the world means nothing if it cannot be kept running in combat conditions. Germany learned these lessons through hundreds of grounded jet fighters scattered across German airfields in 1945. America learned them through systematic analysis of captured aircraft and engines, then built jet fighters that prioritized durability alongside performance. The Me262, magnificent in conception and crippled in execution, taught more through its failures than its successes. The jet fighter that should have changed the war instead changed how military technology is developed, proving that sustainability defeats superiority when extended operations determine victory. In that paradox lies the complete legacy of the Messerschmitt Me262 and its 10-hour engines that promised revolution but delivered only frustration. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.